Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. At this very moment, while your body rests, the solar system is sweeping through the Milky Way at an astonishing pace, about 230 kilometers every second. That is more than 800,000 kilometers per hour. The sun is not suspended in stillness. It is carried along a vast galactic path, guided by gravity, shaped by dark matter, and bound to the combined mass of hundreds of billions of stars. Tonight, we ease into that motion and gently unfold it. Why the solar system travels at this speed. How astronomers measured it with precision. What prevents us from drifting inward toward the massive object at the galaxy's heart. And how many layers of motion your body is quietly riding right now. None of this is speculation. Every value comes from observations that have been tested, repeated, and refined over decades. This journey begins with a simple question. Why must our solar system circle the Milky Way at such tremendous speed? The answer arrives quickly and unmistakably. The sun is not free to choose its path. It is embedded within an immense gravitational field formed by stars, gas, dark matter, and a supermassive black hole at the galaxy's center. That field accelerates the sun forward, locking it into a steady orbit around the Milky Way. Early clues emerged in the early 20th century, when astronomers studying stellar spectra noticed systematic shifts in light that hinted at large-scale galactic motion. By the 1950s, radio observations of hydrogen gas revealed the rotation of the galaxy itself. As instruments improved, measurements from space-based observatories refined the sun's velocity again and again, until it settled near the value we use today, about 230 kilometers per second. This speed exists because the galaxy's gravity demands it. Just as planets remain in orbit because their forward motion balances a star's pull, the sun stays in its galactic lane because its velocity precisely counters the inward gravitational force. If it moved even slightly slower, long-term simulations show it would gradually drift inward toward the crowded region near the galactic core. If it moved faster, it would slowly climb outward, escaping the galaxy's grip. To understand why this balance holds, astronomers study something called the galactic rotation curve, a map showing how orbital speeds change with distance from the center. In the 1970s, Vera Rubin and Kent Ford made a startling discovery while studying spiral galaxies. They found that stars far from the center were moving just as fast as stars much closer in. According to visible matter alone, this should not have been possible. The implication was profound. There had to be additional mass, vast quantities of it, extending far beyond the luminous disk. This unseen structure is now known as the dark matter halo. Without it, the Milky Way simply would not have enough gravity to hold itself together at the speeds we observe. Our solar system moves as fast as it does because visible stars are only part of the story. Dark matter supplies the missing gravitational framework. Observations from gamma-ray telescopes, cosmic microwave background surveys, and large-scale structure studies all support this picture. Most of our galaxy's mass does not shine, yet it governs everything that moves within it. This speed may sound extreme, but it is entirely ordinary in a universe shaped by gravity. The sun's path traces a wide, slow arc around the galaxy. One full circuit takes roughly 200 to 250 million years, a span astronomers call a galactic year. The last time the sun completed such a journey, dinosaurs were only beginning to walk the Earth. When the next one ends, continents will be rearranged and the night sky will look unfamiliar to future eyes. Every object around you participates in this layered motion. Planets circle the sun. The sun circles the galaxy. And the Milky Way itself drifts relative to neighboring galaxies. Mapping this complexity has become possible thanks to precision missions like Gaia, which has measured the positions and motions of more than 1 billion stars with extraordinary accuracy. From that immense dataset, astronomers can reconstruct the sun's exact direction of travel. It is moving toward a point known as the solar apex, in the direction of the constellation Hercules. This result aligns perfectly with earlier measurements made using radio interferometry, where distant quasars serve as fixed reference points against which our motion can be detected. All of these methods agree. The solar system is not wandering. It is flowing along a gravitational current carved by the structure of the galaxy itself. And as you listen, breathe and rest, your body is carried effortlessly within that motion, steady, silent, and unseen. All of these methods together point to a single conclusion. The solar system is not merely circling the galaxy by chance. It is sustaining a precise speed set by a gravitational balance that has remained stable for billions of years. To picture this, astronomers often borrow an idea from basic physics. Imagine an object falling toward a massive body. If it falls straight down, it eventually collides. But if it also moves sideways fast enough, it never reaches the center. Instead, it curves endlessly around it. That is what the Sun is doing. It is constantly pulled inward by the Milky Way's gravity, yet it moves forward quickly enough to keep missing the center. This quiet balance between inward pull and sideways motion is the essence of an orbit. The same principle keeps satellites circling Earth. The difference is scale. Here, the orbit spans tens of thousands of light-years and is shaped by a galaxy rather than a planet. Over the past several decades, researchers have mapped the Milky Way's mass using many independent tracers. Radio surveys of hydrogen gas at a wavelength of 21 centimeters reveal how the galaxy rotates. Observations of carbon monoxide clouds trace dense star-forming regions. Infrared surveys cut through dust to expose hidden structure. All of these measurements converge on the same picture. The Sun resides roughly 26,000 light-years from the galactic center, within a region where dark matter and the combined mass of countless stars dominate the gravitational field. X-ray observations add another layer of confirmation. NASA's Chandra X-ray Observatory has detected extremely hot gas near the galaxy's core, moving with energies consistent with a system of immense mass rotating at high speed. These signals align with predictions made by galactic models long before such measurements were possible. Even more refinement came in recent years. In 2022, the Event Horizon Telescope released the first direct image of Sagittarius A*, the supermassive black hole at the Milky Way's center. That image helped sharpen estimates of the black hole's mass and strengthened orbital models for nearby stars. Some of these stars, tracked for decades by instruments like the Very Large Telescope in Chile, move so rapidly that their paths act as precise probes of the central gravitational field. Their behavior independently confirms the forces shaping the Sun's orbit far beyond them. Our understanding of the Sun's galactic speed has improved steadily over time. Early radio measurements in the mid-20th century suggested values near 250 kilometers per second, though with large uncertainties. By the early 2000s, improved detectors and broader surveys narrowed that estimate closer to 220 kilometers per second. With the arrival of Gaia's ultra-precise stellar catalog, the value settled near 230 kilometers per second, with uncertainty reduced to a fraction of earlier estimates. Each step forward tightened the picture rather than changing it. Despite this immense velocity, the solar system exists in a remarkably calm neighborhood. The Milky Way is not a rigid wheel. It is a living system shaped by slow gravitational interactions. Spiral arms are not solid structures but waves of higher density that drift through the disk. Over tens of millions of years, the solar system passes through different regions, sometimes nearer to star-forming zones, sometimes farther away. Geological records on Earth even hint at possible long-term connections between galactic environment and climate, though this remains an active field of research. What is clear is that large-scale simulations consistently show long-term stability. Models developed using data from NASA's Jet Propulsion Laboratory and the European Southern Observatory incorporate stellar motions, dark matter distributions, and the galaxy's evolving shape. Across billions of years, the result is the same. The Sun's orbit remains steady, and its speed is exactly what that stability requires. Numbers this large can feel distant from human experience. To make them tangible, scientists sometimes translate galactic motion into familiar time frames. At its current speed, the solar system travels roughly 7 billion kilometers each year relative to the galactic center. Over a typical human lifetime, that adds up to hundreds of billions of kilometers. And yet, through all of this motion, Earth quietly completes its gentle yearly path around the Sun. This layered movement is why deep space navigation demands extreme precision. NASA's Deep Space Network communicates with spacecraft like Voyager, Cassini, and New Horizons using reference points far beyond the galaxy. Distant quasars serve as fixed markers against which motion can be measured. Without them, the overlapping motions of Earth, the Sun, and the Milky Way would blur navigation beyond usability. Another striking confirmation comes from the oldest light in the universe. In the late 1970s, scientists studying the cosmic microwave background discovered a subtle temperature difference across the sky. One direction appears slightly warmer, the opposite slightly cooler. This dipole pattern exists because the solar system is moving through space relative to that ancient radiation field at about 370 kilometers per second. When this motion is broken down into components, the Sun's orbital speed around the Milky Way appears clearly within it. Later missions, including WMAP and Planck, confirmed this effect with extraordinary precision. Together, all of these observations tell the same story. The solar system moves at hundreds of kilometers per second because of its position within the Milky Way's gravitational architecture. The galaxy's mass sets the orbital pace, and dark matter ensures that this pace remains high even far from the luminous core. With that foundation established, the next question naturally follows. What exactly maintains this balance? What prevents the solar system from slowly drifting inward towards Sagittarius A*? The answer is both simple and unsettling. If the Sun were moving even slightly slower, the balance would tip. Gravity would begin to win. Over immense spans of time, the solar system would spiral inward, carrying every planet, comet, and grain of dust closer to the galactic center. This reality was not obvious to early astronomers. In the 19th century, measurements of stellar motion hinted that the Sun was moving, but the true scale remained hidden. By the early 20th century, improved spectroscopy revealed patterns that could only be explained by motion within a massive galactic system. Over decades, the concept of orbital velocity took shape. It became clear that motion itself is what prevents collapse. NASA often summarizes it in simple terms. An orbiting object is always falling, but it moves forward fast enough to keep missing what it falls toward. This is true for a satellite circling Earth. It is true for the Moon. And on the grandest scale, it is true for the Sun as it glides endlessly around the heart of the Milky Way. If the Sun were slowed by even a small fraction, the balance would break. A reduction of 10% would be enough for the inward pull of the Milky Way to dominate. The path would no longer close smoothly around the center. Instead, the Sun's trajectory would begin bending inward, slowly at first, then more sharply as gravity gained the upper hand. Over immense spans of time, that inward curve would steepen into a gradual descent toward the galaxy's core. The opposite is also true. If the Sun somehow acquired additional speed, simulations show that its orbit would expand. The solar system would drift outward, rising into the diffuse regions of the galactic halo. Given enough time, it could even escape the Milky Way's gravitational grip entirely. These outcomes reveal an important truth. The Sun's current speed is not arbitrary. It is the precise value required by the mass distribution of the galaxy itself. That distribution extends far beyond what telescopes directly reveal. The Milky Way's gravity is not shaped only by visible stars and glowing gas. It is the combined influence of countless stellar systems, dense molecular clouds, the central black hole, and an enormous halo of dark matter that envelopes the entire galaxy. Without this unseen component, the gravitational pull would be far too weak to sustain the motion we measure. At the heart of the Milky Way lies Sagittarius A*, now firmly established as a supermassive black hole. Observations from the Very Large Telescope in Chile and the Keck Observatory in Hawaii have tracked the motion of stars packed tightly around it for more than 20 years. These stars form a dense cluster, and among them one stands out in particular. Known as S2, it completes a full orbit in only 16 years. Near its closest approach, it accelerates to several thousand kilometers per second. Such extreme motion can only be explained by a compact object containing about 4 million times the mass of the Sun. Andrea Ghez, one of the scientists who led these measurements, summarized the results simply. The orbits reveal an extraordinary mass confined to a very small region. That mass dominates the inner core of the galaxy, yet it does not outweigh the combined influence of stars, gas, and dark matter spread throughout the disk and halo. Far from the center, where the solar system resides about 26,000 light-years away, gravity remains strong but balanced. The orbital speed of roughly 230 kilometers per second is exactly what this environment demands. The Gaia mission has played a crucial role in refining this picture. By charting the positions and motions of more than 1 billion stars, Gaia has allowed astronomers to reconstruct the Milky Way's gravitational field in unprecedented detail. From this vast dataset, scientists can calculate not only how fast the Sun must move to remain in orbit, but also how stable that orbit has been across billions of years. The physics behind this balance becomes clearer when viewed closer to home. Satellites circling Earth must travel at a specific speed to avoid falling back down. In low Earth orbit, that speed is about 8 kilometers per second. Any slower, and the satellite descends into the atmosphere. Any faster, and it climbs into higher orbits or escapes entirely. The solar system follows the same rule, scaled up to a galaxy-sized stage. Early attempts to measure the Milky Way's mass revealed just how puzzling this system was. In the early 20th century, astronomers like Jan Oort studied how stars moved above and below the galactic plane. Their measurements showed that visible matter alone could not account for the observed motions. Something unseen was contributing additional gravitational pull. Over time, this missing component came to be known as dark matter. Dark matter does not shine, absorb light, or emit radiation. Its presence is inferred entirely through gravity. When radio telescopes measured the rotation of hydrogen gas far beyond the visible edge of the Milky Way, they found velocities far higher than luminous matter could explain. These observations strengthened the conclusion that the Sun's orbit is maintained by the galaxy's full mass, not just the portion we can see. This reveals the nature of our orbital stability. The solar system is not balanced on a knife's edge. It is embedded within a broad and dynamic gravitational field. Passing stars, giant molecular clouds, and star clusters can nudge the orbit slightly over time. Yet large-scale simulations conducted at NASA's Jet Propulsion Laboratory show that the Milky Way's structure creates a remarkably durable path. As long as the Sun's speed remains near its current value, the orbit remains secure. Multiple lines of evidence reinforce this conclusion. In the late 20th century, measurements of the cosmic microwave background revealed a subtle temperature pattern across the sky. This dipole signal arises because the solar system is moving relative to the universe's oldest light. When researchers separated this motion into components, the contribution from the Sun's galactic orbit emerged clearly. Later missions, including WMAP and Planck, confirmed the same value with extraordinary precision. Long baseline radio interferometry added further confirmation. By linking radio telescopes across continents, astronomers used distant quasars as fixed reference points. Against these anchors, they measured the Sun's motion with remarkable accuracy. Decades of effort were required to eliminate atmospheric distortions and calibration errors, but the final results aligned precisely with predictions from galactic dynamics. NASA often describes this motion as continuous free fall. The Sun is constantly being pulled inward by gravity while moving sideways fast enough that its path curves endlessly around the center instead of plunging inward. If the forward speed dropped, gravity would dominate. If it increased, the orbit would stretch outward. The balance is exact, yet resilient, maintained by forces that operate steadily over cosmic time. Computer simulations have reinforced this understanding. Large-scale projects such as the Illustris and Illustris TNG simulations model galaxy formation using detailed physics, including gas dynamics, star formation, and dark matter. Within these virtual galaxies, objects located at distances similar to the Sun's always require orbital speeds close to what we observe. Across simulations and observations alike, the same pattern emerges. Gaia added one final refinement. Its data reveal that the Sun's orbit is not perfectly circular. It is slightly elliptical, meaning the solar system drifts closer to and farther from the galactic center over very long periods. These variations produce small changes in speed, but they remain well within the stable range dictated by the galaxy's mass distribution. Taken together, a century of observation, theory, and simulation paints a consistent picture. The Sun is not held in place by a single dominant force. Its motion is shaped by the central black hole, the dense stellar bulge, the sweeping disk of stars and gas, and the vast dark matter halo surrounding them all. These components combine to create a gravitational field that demands a specific orbital speed. The Sun moves at that speed, no more and no less. With the solar system settled into this precise balance, a deeper mystery comes into focus. The forces shaping our motion do not end at the visible edge of the galaxy. Beyond it lies a mass distribution so influential that it reshapes gravity itself. And that leads us forward. Part 3. Why do the outer regions of the Milky Way rotate too quickly for visible matter to explain? The realization arrives quietly, but its implications are profound. Far from the galactic center, stars continue to move at nearly the same speed as those much closer in. According to classical physics, they should slow down. They do not. Instead, the rotation curve remains flat, defying expectations and revealing that much of the galaxy's mass lies hidden from view. This is where the universe breaks one of our simplest rules, and begins to show us what it is really made of. If the Sun were slowed by even a small margin, just 10%, the balance that keeps it circling the Milky Way would fail. The inward gravitational pull of the galaxy would overpower its sideways motion. What is now a stable path would begin to bend inward, slowly at first, then with increasing urgency as the Sun drifted closer to the galactic core. If, instead, the Sun somehow gained extra speed, long-term simulations predict the opposite fate. Its orbit would gradually expand, lifting it into the outer halo until the galaxy's gravity could no longer hold it. The Sun would eventually escape altogether. The speed that prevents either outcome is not set by visible stars alone. It is determined by the combined mass of the Milky Way. Billions of stars, vast molecular clouds, the central black hole, and an enormous halo of dark matter that extends far beyond what telescopes can see. Without this unseen mass, the forces acting on the solar system would be far too weak to explain the motion we measure. At the galaxy's center lies Sagittarius A*, confirmed to be a supermassive black hole through decades of observations using instruments such as the Very Large Telescope in Chile and observatories in Hawaii. Astronomers have tracked the motion of stars packed tightly around this region, known as the Central Star Cluster. One star in particular, called S2, completes a full orbit in only 16 years. Near its closest approach, it reaches speeds of several thousand kilometers per second. Such extreme motion can only be explained by a compact object weighing about 4 million times more than the Sun. After years of careful measurements, one of the leading researchers in this field explained that these stellar paths reveal an extraordinary concentration of mass in a remarkably small volume. While this central object dominates the innermost region of the galaxy, it does not outweigh the combined influence of stars, gas, and dark matter spread throughout the vast galactic disk. The solar system resides roughly 26,000 light-years from this center. At that distance, gravity exerts a steady but balanced pull. The Sun's orbital speed, about 230 kilometers per second, is precisely what is required to remain on its path. The European Space Agency's Gaia mission has been crucial in refining this picture. By mapping the positions and motions of more than 1 billion stars, Gaia has provided an unprecedented view of the Milky Way's gravitational structure. From this data, astronomers can calculate not only how fast the Sun must move, but how stable its orbit has remained over billions of years. The same principles apply closer to home. A satellite circling Earth must travel at a specific speed to stay in orbit. In low Earth orbit, that speed is about 8 kilometers per second. Any slower, and the satellite falls back toward the atmosphere. Any faster, and it climbs into a higher orbit or escapes entirely. The solar system follows this identical rule, scaled up to galactic proportions. Early attempts to measure the Milky Way's mass revealed a serious problem. In the early 20th century, astronomers studying the vertical motion of stars above and below the galactic plane discovered that visible matter alone could not produce the required gravitational pull. Something else had to be present: mass that did not follow the distribution of stars or gas. Over time, this missing component became known as dark matter. Dark matter does not emit or absorb light, but its presence is revealed through gravity. When radio telescopes measured the rotation of hydrogen gas in the outer Milky Way, they found velocities far higher than expected. These findings showed that the Sun's orbit is sustained by the full mass of the galaxy, not just what can be seen. Despite this complexity, the solar system's orbit is remarkably resilient. It is not balanced on a knife's edge. Simulations performed at NASA's Jet Propulsion Laboratory show that although encounters with massive gas clouds or passing stars can slightly alter the path, the overall structure of the Milky Way provides a stable corridor. As long as the Sun's speed remains near its present value, the orbit endures. This understanding rests on decades of independent discoveries. In the late 1970s, measurements of the cosmic microwave background revealed that the solar system is moving relative to this ancient radiation. Part of that motion comes from our journey around the galaxy. Later missions refined these measurements, and the results matched those obtained from stellar motions and radio observations. Another breakthrough came from long baseline radio interferometry, which links telescopes across continents. By tracking the Sun's position relative to distant quasars, astronomers measured its motion with extraordinary accuracy. These observations confirmed the speed required to sustain our orbit. The process was not easy. In the 1980s, astronomers working with large radio arrays spent years separating the Sun's motion from local stellar movements. Atmospheric effects, timing errors, and calibration challenges had to be eliminated. When the final results emerged, they matched theoretical predictions within a narrow margin, reinforcing confidence in the models. NASA often describes this motion as continuous free fall. The Sun is constantly falling toward the galactic center, but it moves sideways fast enough that the fall curves into a loop rather than a plunge. If that forward motion decreased, gravity would dominate. If it increased, the orbit would stretch outward. The balance is precise, yet stable over immense time spans. Large-scale simulations of galaxy formation, such as those from the Illustrious and Illustrious TNG projects, further support this picture. When these models include gas dynamics, stellar evolution, and dark matter, they produce galaxies that closely resemble the real Milky Way. Objects located where the Sun resides consistently require orbital speeds matching what we observe. Gaia has added another refinement. Its data shows that the Sun's orbit is not perfectly circular, but slightly elliptical. Over long periods, the solar system drifts closer to and farther from the galactic center. These variations change the Sun's speed slightly, yet always within the range that preserves stability. Taken together, a century of observation and simulation reveals a clear truth. The Sun's motion is governed not by a single object, but by the collective gravity of the entire galaxy. The central black hole, the dense inner bulge, the sweeping disk of stars and gas, and the vast dark matter halo. The Sun moves at exactly the speed this gravitational landscape demands. From this perspective, a larger question naturally arises. The forces shaping our orbit do not stop at the edge of the Milky Way. They extend outward into even greater structures, setting the stage for what comes next. Part 3. Why do the outer regions of the Milky Way rotate too fast to be explained by visible matter? At the Sun's distance, the galaxy rotates far faster than its visible mass should allow. According to classical calculations, stars farther from the center should move more slowly. They do not. Instead, their speeds remain nearly constant, revealing a deep conflict between observation and expectation. Hints of this problem appeared as early as the 1930s, when astronomers measured stellar motions in nearby galaxies. The data was limited, but the pattern was troubling. By the 1970s, improved instruments allowed a systematic study of hydrogen gas rotating in galactic disks. The results were unmistakable. Rotation curves rose near the center, then flattened and stayed flat across vast distances. This pattern appeared again and again, across galaxies of many shapes and sizes. Later radio observations confirmed the same behavior far beyond the visible edge. If only visible matter were present, galaxies like the Milky Way would gradually lose their outer stars. The fact that they remain intact demands an additional, dominant mass component. This mass forms a roughly spherical halo extending hundreds of thousands of light-years beyond the disk. It does not interact with light, but it shapes motion everywhere. Space missions mapping stellar positions and velocities strengthened this conclusion, revealing motions that match predictions for a galaxy embedded in a massive dark matter halo. Additional support came from gamma-ray observations, gravitational lensing, and studies of colliding galaxy clusters, where mass was observed separating from visible matter during collisions. These results provided some of the clearest empirical evidence that unseen matter governs cosmic motion. Simulations of galaxy formation confirm the same lesson. Without dark matter, galaxies collapse or rotate incorrectly. With it, their behavior matches reality. Dark matter stabilizes galaxies and influences how they form from the earliest times. The distribution of this invisible mass remains an active area of research. Data suggests the halo may be slightly elongated, shaped by interactions with nearby galaxies. Ripples in the Milky Way's disk appear to trace the response of this unseen structure. Even observations of early galaxies show similar rotation patterns, implying that dark matter shaped motion almost immediately after the universe began. All evidence converges on the same conclusion. Without dark matter, the Milky Way could not rotate as it does, nor remain intact for over 13 billion years. And beyond galactic rotation lies an even more startling realization. Part 4. How many layers of motion are you riding on right now? Even while you sit perfectly still, you are moving, carried through space by multiple overlapping motions. Earth spins beneath your feet, racing eastward at over 1,600 kilometers per hour at the equator. This rotation was confirmed long ago by a simple pendulum experiment, and today it is measured with exquisite precision using distant quasars as reference points. These layered motions continue outward, stacking one upon another, forming a journey far greater than anything our senses can perceive. The second layer of motion comes from Earth's path around the Sun. Each year, our planet traces a wide orbit roughly 150 million kilometers from its star, moving through space at nearly 30 kilometers per second. This motion was not assumed, it was measured. In the 19th century, astronomers finally detected stellar parallax, the tiny apparent shift of nearby stars against distant ones as Earth moved from one side of its orbit to the other. The effect was extremely small, only fractions of an arcsecond, yet it provided the first direct, quantitative proof that Earth was traveling through space on a vast circular path. Beyond Earth's orbit lies the third layer. The Sun itself is in motion, circling the center of the Milky Way at a speed of about 230 kilometers per second. One complete journey takes hundreds of millions of years. Data from the Gaia mission has mapped this motion in extraordinary detail, charting not only the Sun's path but also its gentle rise and fall through the galactic plane. Rather than moving on a perfectly flat track, the Sun oscillates slightly above and below the disk, guided by the galaxy's overall gravitational structure. The fourth layer reveals an even broader movement. The Milky Way is not fixed in the universe. It drifts relative to neighboring galaxies and relative to the faint glow left behind by the Big Bang itself. Measurements made by space-based observatories showed that the solar system is moving at roughly 370 kilometers per second compared to this ancient background radiation. This motion produces a subtle temperature contrast across the sky, known as the cosmic microwave background dipole. One direction appears slightly warmer, the opposite slightly cooler, a result of the Doppler effect acting on the oldest light in existence. Later missions refined this measurement, confirming both the speed and direction with remarkable precision. Behind these discoveries is a long tradition of meticulous measurement. Radio telescopes spread across continents operate together using very long baseline interferometry. By comparing the arrival times of radio signals from distant quasars, scientists can detect motions of Earth, the Sun, and the galaxy itself. These timing differences are measured in billionths of a second, yet they reveal movements spanning continents and entire star systems. The importance of accounting for every layer of motion became clear during the early days of deep space exploration. When the Voyager spacecraft were launched in the late 1970s, engineers had to consider Earth's rotation, Earth's orbit, the Sun's galactic motion, and the Milky Way's broader drift. Ignoring even one layer would have sent the spacecraft far off course. Precision required acknowledging that nothing in space is truly stationary. These motions also interact in subtle ways. Earth's rotation changes slightly over time due to tidal forces from the Moon. Shifts in mass within the planet, such as melting ice sheets or major earthquakes, alter rotation by measurable amounts. NASA routinely tracks these variations to maintain the accuracy of navigation systems and satellite positioning. What seems imperceptible in daily life becomes critical when measuring motion on a planetary scale. When all layers are combined, Earth's spin, Earth's orbit, the Sun's galactic motion, and the Milky Way's movement through space, the resulting velocity reaches hundreds of kilometers per second. This is not a metaphor or an abstraction. It is a directly measured fact supported by decades of observation. These layered motions shape Earth's environment as well. As the solar system travels through the interstellar medium, it encounters regions of different density and magnetic structure. Data from the Voyager probes show changes in particle flow as they move beyond the boundary dominated by the Sun's influence. Scientists use this information to understand how cosmic radiation reaches Earth and how the heliosphere shields the planets. Considering all these motions together reveals a striking perspective. The surface beneath your feet is part of a coordinated journey shaped by gravity on every scale. This combined motion also influences how Earth is oriented in space. The interstellar magnetic field shifts relative to our planet, and the heliosphere changes shape as the solar system moves through surrounding plasma. Observations show that this boundary is dynamic, molded by motion rather than fixed in place. Beyond the Milky Way, even larger structures exert their pull. Our galaxy and its neighbors move together within the local group, drifting toward a massive region of gravitational influence often called the Great Attractor. Surveys of distant galaxies show large-scale flows spanning tens of millions of light-years, all guided by invisible concentrations of mass. Reaching this understanding required a profound shift in perspective. For centuries, Earth was assumed to be at rest. Gradually, evidence accumulated showing that Earth rotates, orbits the Sun, and travels through the galaxy. Each step forward depended on more precise tools, atomic clocks, laser ranging, deep space communication networks, all capable of measuring time and distance with extraordinary accuracy. Every layer of motion has been confirmed independently. Earth's rotation is tracked using satellite gyroscopes. Earth's orbit is measured through radar reflections and laser ranging to the Moon. The Sun's galactic motion is mapped through stellar velocities. The Milky Way's movement relative to the cosmic microwave background is detected through space-based microwave measurements. Together, these methods form a consistent and reliable picture. Engineers responsible for spacecraft navigation often emphasize a simple rule: accuracy demands accounting for every motion involved. A spacecraft bound for another planet must be launched from a rotating world toward a moving target while both travel around the Sun. Every velocity matters. Viewed together, these motions describe a universe that is dynamic yet predictable. The forces guiding Earth's journey are steady, governed by physical laws understood for centuries. Though the scales involved are immense, they allow stability over billions of years. And yet, a deeper question remains. If we are moving along with the system we are trying to measure, how do we determine our own speed from inside it? Part 5. How do we measure the solar system's motion through the Milky Way while being carried along with it? The answer lies in signals so subtle that a temperature change smaller than 1/1000th of a degree, or a shift of 1/100000th of a second in radio timing, becomes meaningful. Astronomers have learned to extract motion from these delicate clues without ever stepping outside the galaxy. The most direct evidence comes from the cosmic microwave background, the oldest light in the universe. When this radiation was mapped in detail, scientists found a faint but unmistakable temperature pattern. One direction in the sky appeared slightly warmer, the opposite slightly cooler. The difference was tiny, yet profound. It revealed both the direction and speed of the solar system's motion through space. That ancient light, stretched across the entire sky, became a cosmic reference frame, one against which our journey could finally be measured. This pattern appears because motion alters light itself. As an observer moves forward, waves arriving from ahead are slightly compressed, while those from behind are gently stretched. This phenomenon, known as the Doppler effect, leaves a measurable imprint across the sky. Over time, increasingly precise missions refined this picture. NASA's Wilkinson Microwave Anisotropy Probe revealed the dipole structure with far greater resolution. Later, ESA's Planck spacecraft, launched in 2009, delivered the most detailed map of the cosmic microwave background ever produced. Its instruments were sensitive enough to detect variations corresponding to motions of only a few kilometers per second. When results from these missions were combined, scientists found that a portion of the observed motion relative to the cosmic background aligns with the Sun's orbit around the Milky Way, measured at roughly 230 kilometers per second. Yet the background radiation alone cannot tell us how fast the Sun moves within the galaxy. It reveals motion relative to the universe as a whole. To isolate the Milky Way's contribution, astronomers turn to independent measurements drawn from stars, gas, and distant radio sources. This is where the Gaia mission becomes essential. Launched in 2013, Gaia was designed to construct a three-dimensional map of the Milky Way with unprecedented precision. Its detectors track minuscule changes in stellar positions as Earth circles the Sun. These shifts expose how stars move relative to the solar system. By measuring more than 1 billion stars, Gaia reveals the internal flow of the galaxy itself. If the solar system were stationary, nearby stellar motions would appear evenly distributed. Instead, Gaia detects a systematic drift that reflects our own movement through the stellar background. From these measurements, astronomers calculate the Sun's motion toward a direction known as the solar apex, located near the constellation Hercules. This result closely matches earlier findings obtained through radio astronomy. Using long baseline interferometry, widely separated radio telescopes operate together as a single instrument. By comparing the arrival times of signals from distant quasars, scientists can pinpoint Earth's position with extraordinary accuracy. The tiny timing differences reveal how Earth and the solar system move through space. The development of long baseline interferometry, often abbreviated VLBI, stands as one of the quiet achievements of modern astronomy. Beginning in the 1970s, observatories synchronized antennas thousands of kilometers apart using atomic clocks. Quasar signals, emitted billions of years ago, arrive at each station with slight delays. These offsets reveal Earth's motion within the solar system and the Sun's motion within the galaxy. Over decades, VLBI measurements helped refine the solar system's orbital speed with remarkable precision. Among the most important facilities is the Very Long Baseline Array, stretching from Hawaii to the Caribbean. Operating continuously, it observes distant quasars and star-forming regions inside the Milky Way. The data reveal predictable changes driven by Earth's orbit, the Sun's galactic path, and the rotation of the galaxy itself. These results reinforce values derived from Gaia and the cosmic background dipole. Spectral measurements of gas provide another critical line of evidence. Neutral hydrogen emits radio waves at a wavelength of 21 centimeters, allowing astronomers to trace motion throughout the Milky Way. When hydrogen moves toward Earth, the signal shifts slightly upward in frequency. When it moves away, it shifts downward. Mapping these shifts across the sky produces a detailed velocity field that includes both galactic rotation and the Sun's movement through it. Observations from instruments such as the Green Bank Telescope and the former Arecibo Observatory played a central role in constructing these maps. All of this rests on principles established centuries ago. When Joseph Doppler first described how motion alters frequency, astronomers quickly recognized its power. Yet they could not have imagined a future where the same idea would be applied to radiation left from the Big Bang or signals transmitted by quasars billions of light-years away. Modern Doppler techniques now allow scientists to detect motions of only a few meters per second across astronomical distances. Each method contributes a piece of the puzzle. The cosmic microwave background defines motion relative to the universe itself. Gaia reveals how nearby stars shift against us. Radio interferometry tracks Earth's position through precise timing. Hydrogen mapping exposes the motion of gas across the galaxy. Together, these independent approaches converge on the same conclusion. The Sun orbits the Milky Way at a speed of about 230 kilometers per second. The path to this understanding was gradual. In the late 1990s, astronomers using VLBI combined parallax measurements of star-forming regions with models of galactic rotation. Their work revealed small inaccuracies in earlier estimates of the Sun's location within the Milky Way. Correcting those values refined the calculated orbital speed. Later Gaia data improved stellar distances even further, tightening the measurement once again. One long-standing challenge involved determining the exact distance to the galactic center. For years, estimates ranged between 26 and 28,000 light-years. This uncertainty mattered because orbital speed depends on both distance and mass distribution. The breakthrough came from observations of a star known as S2, which orbits extremely close to Sagittarius A star. Over 16 years, astronomers tracked its full orbit using infrared telescopes. The motion of S2 revealed the precise mass of the central black hole and fixed the scale of the Milky Way. The resulting values confirmed earlier speed estimates rather than overturning them. Spacecraft have also contributed indirectly. Instruments aboard the Voyager probes detected changes in cosmic rays and plasma as they crossed the boundary of the heliosphere. These variations help scientists understand how the solar system interacts with its galactic surroundings. The Interstellar Boundary Explorer mission added further detail by mapping energetic neutral atoms that trace the shape of the Sun's magnetic bubble. These observations refine models of how motion through the galaxy shapes our local environment. Across all techniques, the outcome is consistent. Independent measurements point to the same orbital speed. The confidence in this value comes not from any single instrument, but from agreement across many methods. NASA emphasizes this approach, noting that modern astrophysics depends on cross-verification between observatories, spacecraft, and analytical models. As measurement techniques improved, researchers began applying machine learning tools to Gaia's massive datasets. These algorithms uncover subtle patterns in stellar motion, revealing how stars respond to spiral arms, gravitational disturbances, and the underlying mass of the galaxy. Each insight reinforces the same picture of the Sun's motion. Advances in atomic clocks, space-based telescopes, and radio receivers have pushed precision to extraordinary levels. Atmospheric distortion is avoided. Timing errors are minimized. Faint signals from across the universe are captured with clarity. Each improvement strengthens confidence in the measurement. Viewed together, the evidence forms a coherent whole. We know how fast the solar system moves because the universe provides multiple reference frames, ancient radiation, distant galaxies, nearby stars, all pointing to the same motion shaped by the Milky Way's gravity. With that understanding in place, attention shifts to time rather than speed. If the Sun's motion through the galaxy can be measured so precisely, the next question becomes one of duration. Part 6. What does a single galactic year look like for the Sun and its planets? The remarkable truth is that all of recorded human history has unfolded during only a small fraction of one galactic orbit. A single revolution around the Milky Way takes roughly 200 to 250 million years. During that span, entire eras of Earth's past have emerged, transformed, and disappeared. The concept of a galactic year developed slowly. Early 20th century measurements of stellar motion revealed that the Sun was not fixed in space. By the mid-20th century, radio observations of hydrogen gas exposed the rotating structure of the Milky Way. Later missions refined these findings, converging on a consistent orbital period supported by multiple lines of evidence. To grasp the scale, compare it with Earth's own year. Our planet completes one orbit around the Sun every 365 days, moving at about 30 kilometers per second. Now magnify that motion to the galactic scale. At a distance of roughly 26,000 light-years from the center, the Sun follows an immense curve shaped by the mass of hundreds of billions of stars and an even larger halo of dark matter. Completing this path requires hundreds of millions of years. The Sun's journey is not confined to a flat plane. Instead, the solar system slowly rises above and dips below the galactic disk in a long oscillation lasting tens of millions of years. This motion was hinted at in early velocity studies and later confirmed by space-based astrometry. Gaia's three-dimensional map reveals this vertical rhythm with striking clarity. As the Sun moves through different regions of the galaxy, the surrounding environment changes. Star density, gas concentration, and radiation levels vary depending on position relative to the galactic plane. Researchers studying Earth's deep past have explored whether these variations influence long-term conditions on our planet. While many questions remain open, the changing interstellar environment is well documented. A galactic year also reframes Earth's biological history. When the Sun last completed a full orbit, Earth's continents were joined into the supercontinent Pangaea. Dinosaurs were just beginning to spread. Mammals, birds, and flowering plants had yet to appear. As the solar system advanced along its path, life diversified, oceans shifted, and mountains rose. NASA often illustrates this scale by placing major events from Earth's history along the Sun's orbital path. The asteroid impact that ended the age of dinosaurs occurred during the later portion of the current orbit. Earlier stages coincide with the rise of ancient reptiles. These associations do not imply cosmic cause, but they highlight the contrast between human time and galactic time. From this perspective, the Sun's motion becomes more than a number. It becomes a rhythm, a slow, steady cycle unfolding while worlds change beneath it. Understanding a galactic year required measurements of extraordinary precision. Astronomers needed to know how fast the Sun moves and how mass is distributed throughout the Milky Way. The most accurate information about the galaxy's center came from observations of a single star, S2, orbiting the compact object known as Sagittarius A star. For more than 2 decades, infrared telescopes such as those at the Keck Observatory and the Very Large Telescope tracked S2 as it completed a full orbit. Its motion revealed the mass of the object it encircles, allowing astronomers to calculate how stars should move at different distances from the galactic center. From this framework emerged refined estimates of the Sun's orbital speed and the length of one galactic year. The Gaia mission transformed this picture. By measuring the positions and motions of more than 1 billion stars, Gaia mapped the Milky Way's rotation with unprecedented resolution. Its 2018 data release refined the Sun's trajectory and revealed that our solar system oscillates slowly above and below the galactic plane. These results confirmed earlier models while adding subtle details about the Sun's current upward motion through the disk. The idea of a galactic year also connects to motions far larger than the Sun's orbit alone. The Milky Way itself is moving toward the Andromeda galaxy within the local group, and together through an even larger structure known as the Laniakea supercluster. These layered motions place the Sun's journey within a vast hierarchy of cosmic movement. One of the earliest insights into galactic mass came in the 1920s from the work of Jan Oort. By studying how stars move perpendicular to the galactic plane, he estimated the density of matter near the Sun. His calculations showed that visible stars could not provide enough gravity to explain the observed motions. This was among the first strong indications that unseen matter plays a major role in the galaxy. Later research confirmed the presence of a dark matter halo surrounding the Milky Way. This invisible structure shapes the Sun's orbit and contributes significantly to the length of a galactic year. The Sun's motion through this gravitational framework also influences the heliosphere, the vast bubble formed by the solar wind. As the solar system passes through regions of varying interstellar density, the heliosphere subtly changes shape. NASA's Interstellar Boundary Explorer has mapped these variations by detecting energetic neutral atoms produced at its boundary. Observations from the James Webb Space Telescope add a deeper historical context. JWST has imaged young galaxies from the early universe that already show rotational structures similar to the Milky Way. These findings suggest that ordered orbits like the Sun's have existed since the universe was very young, linking present-day motion to ancient cosmic processes. Understanding a galactic year also requires understanding how galaxies form. Spiral arms are not rigid structures but density waves, created by the collective motion of stars and gas. As the solar system moves through these arms, it encounters regions of enhanced star formation. Such passages occur several times during one galactic orbit, and researchers have explored possible links between these crossings and long-term patterns in Earth's geology and biology. Although many questions remain open, the consistency of astronomical evidence provides a stable framework for understanding the Sun's motion. The idea that the solar system completes one orbit every 200 to 250 million years places human history into a profound perspective. Every major change in Earth's climate, continents, and life has occurred during only a small fraction of this immense journey. Carl Sagan once described Earth as a mote of dust suspended in a sunbeam. The concept of a galactic year reinforces that image, grounding it in measurable motion across vast spans of time. Yet this long journey also defines something immediate: our location. The solar system does not drift through empty space. It moves through a specific region of the Milky Way, one with its own density, activity, and risks. This leads to a deeper question. Is our solar system traveling through a dangerous part of the galaxy, or does it occupy a rare safe zone? A small shift of just a few thousand light-years inward or outward would place Earth in regions dominated by frequent supernovae, dense star clusters, and intense radiation. Instead, the Sun lies neither at the center nor at the edge, but within a narrow band astronomers call the Galactic Habitable Zone. This idea emerged gradually. Early in the 20th century, many astronomers believed the Sun lay near the galactic center. It was only through the work of Harlow Shapley, using globular clusters as tracers, that scientists realized the Sun occupies a relatively quiet region far from the core. Near the galactic center, stellar density is extreme. Millions of stars crowd into small volumes, supernovae occur frequently, and black holes and neutron stars emit intense radiation. NASA's Chandra X-ray Observatory has revealed this region as turbulent and violent, an environment hostile to stable planetary systems. The Sun, by contrast, lies about 26,000 light-years from the center, within the Orion spur between two major spiral arms. Spiral arms are rich in gas and massive stars, many of which end their lives in powerful explosions. Being located between arms significantly reduces Earth's exposure to these hazards. The Galactic Habitable Zone was formalized in the late 20th century by researchers such as Guillermo Gonzalez and Donald Brownlee. They showed that regions too close to the center are dangerous, while regions too far out lack the heavy elements needed to form rocky planets. The Sun formed in a narrow band where metallicity and stability are balanced. Heavy elements are forged in supernovae, but too many explosions would sterilize planetary surfaces. Too few would prevent planets like Earth from forming at all. The Milky Way's metallicity gradient reflects this balance, and the Sun's birthplace lies within an optimal zone. Observations from JWST confirm that planets with atmospheres form most readily in regions similar to our own. Gravitational stability is another factor. In dense stellar clusters, close encounters can disrupt planetary systems, eject planets, or trigger comet showers. Gaia data show that only a handful of stars have passed within a light-year of the Sun over millions of years. In dense clusters, such encounters are routine. The solar system's geological record hints at these influences. Some mass extinctions and climate shifts may correlate with passages through slightly denser regions of the galaxy, though these connections remain debated. Variations in cosmic ray flux, monitored for decades by NASA's ACE spacecraft, may also reflect the Sun's movement through the interstellar medium. The heliosphere acts as a protective shield, but its size changes as interstellar conditions vary. Voyager 1 and Voyager 2 have shown that denser environments compress this shield, allowing more cosmic rays to reach Earth. At present, the solar system travels through the local interstellar cloud, a region of moderate density and relative stability. Spiral arm crossings are of particular interest. These occur roughly every 100 million years and may disturb the distant Oort cloud, increasing comet activity. Gaia's future data will clarify the Sun's path relative to these arms and whether such events influenced Earth's past. Other hazards, such as gamma-ray bursts, are more common in regions of active star formation. NASA's Fermi Gamma Ray Space Telescope has mapped their distribution, showing that the Sun's location avoids most high-risk zones. The solar system also lies far from the galactic bar, whose gravitational influence can destabilize stellar orbits. For much of history, astronomers debated the Sun's precise location within the Milky Way. Radio observations of hydrogen gas finally revealed the galaxy's spiral structure, confirming that the solar system resides in a relatively calm gap between arms. That quiet placement, neither central nor remote, appears to be one of the most important reasons Earth has remained habitable for billions of years. Gaia has refined this picture with extraordinary precision. By measuring the positions and motions of stars across the sky, the mission allows astronomers to reconstruct the structure of the Milky Way in remarkable detail. The data show that the Sun's orbit keeps it at a measured distance from the galaxy's most active regions. That distance is not vast, but it is sufficient to reduce frequent exposure to high-energy events that could threaten complex life. Carl Sagan captured the fragility of this placement when he wrote, "We live on a mote of dust suspended in a sunbeam." In scientific terms, this image reflects how the solar system occupies a narrow region where conditions remain within the limits required for biological complexity to persist. The rate of nearby supernovae, the density of the interstellar medium, and the stability of stellar orbits all contribute to this delicate balance. Observations from the James Webb Space Telescope add another dimension. JWST has revealed galaxies at many stages of evolution, including environments far more chaotic than the Milky Way's present configuration. These comparisons emphasize the relative stability of our galaxy and the fortunate nature of our position within it. Yet, our location is not determined by chance alone. The Milky Way itself is in motion, responding to gravitational forces far larger than its own structure. That motion places our galaxy within a vast stream of galaxies flowing together through space. Part 8. Why is the Milky Way speeding toward the Great Attractor and the Lania Chaos supercluster? The first surprise emerges when we widen our view. The entire Milky Way, its stars, planets, nebulae, and dark matter halo, is moving through space at hundreds of kilometers per second toward a region astronomers call the Great Attractor. This is not a local drift. It is part of an immense gravitational flow involving thousands of galaxies, all moving as if drawn toward a hidden valley in the fabric of the universe. This realization did not arrive all at once. In the 1970s, astronomers began noticing that nearby galaxies displayed peculiar velocities. They were not simply following the smooth expansion of the universe. Many deviated from the expected Hubble flow, appearing to move toward a region in the direction of the constellations Centaurus and Norma. These motions suggested the presence of a massive structure exerting a powerful gravitational pull. In the 1980s, data from the infrared astronomical satellite and ground-based surveys revealed why this structure had remained hidden. It lay behind the dense dust of the Milky Way's disk, where optical telescopes could see very little. Infrared and radio observations, however, began to expose a dense concentration of galaxies now known as the Great Attractor. Its gravitational influence is strong enough to affect the entire local group, including both the Milky Way and Andromeda. Later observations using X-ray telescopes such as NASA's Chandra Observatory and ESA's XMM Newton detected vast reservoirs of hot gas in this region, allowing astronomers to estimate its mass more accurately. These studies showed that the Great Attractor contains multiple galaxy clusters and enormous quantities of dark matter. Yet, even this mass did not fully account for the observed motions. A major breakthrough came in 2014, when Brent Tully and colleagues published a detailed map of cosmic flows based on galaxy distances and velocities. Using data from the Cosmic Flows 2 survey, they revealed that the Milky Way is part of a far larger structure, the Lania Chaos supercluster. Lania Chaos spans roughly 500 million light-years and contains more than 100,000 galaxies. Tully described the discovery by saying that astronomers were no longer just mapping where galaxies are, but where they are going. The trajectories of these galaxies converge toward a central region within Lania Chaos, showing that gravity on enormous scales shapes the motion of entire galaxy groups. These flow patterns are revealed by deviations from cosmic expansion. In a uniformly expanding universe, galaxies should recede from one another at speeds proportional to their distance. When a galaxy moves faster or slower than expected, the difference is attributed to gravitational influence. By mapping these deviations across space, astronomers reconstruct the large-scale gravitational landscape. NASA and ESA missions contribute to this effort through precise distance measurements. Cepheid variable stars, type Ia supernovae, and other standard candles provide reliable distances to galaxies. Combined with redshift data, these measurements reveal the peculiar velocities that define cosmic flows. The resulting maps show that the Milky Way, the Virgo cluster, and neighboring galaxies all stream toward the Great Attractor, whose center lies near the Norma cluster, an immense assembly of galaxies hidden behind the Milky Way's dust. Radio telescopes such as the Parkes Observatory and the Australia Telescope Compact Array revealed galaxies in this obscured region, known as the Zone of Avoidance, completing the map of local structure. Even so, the flow does not end there. Further analysis shows that motion continues beyond the Great Attractor toward an even more massive region called the Shapley concentration, located about 650 million light-years away. This distant supercluster likely contributes significantly to the gravitational pull felt by the Milky Way and its neighbors. Understanding this motion requires recognizing how matter is arranged on cosmic scales. Galaxy clusters are the most massive gravitationally bound objects in the universe. When they group together, they create deep gravitational basins that influence galaxies tens of millions of light-years away. The discovery of Laniakea reframed our understanding of cosmic geography. Rather than existing in isolation, the Milky Way is embedded in a network of filaments and voids. Within this structure, galaxies flow toward dense regions and away from vast underdense areas, forming patterns that resemble currents in a cosmic ocean. One striking feature of this landscape is the dipole repeller, a large region of unusually low density located opposite the Great Attractor. Observations suggest that galaxies are simultaneously pulled toward dense regions and pushed away from voids. Data from the cosmic flows 3 catalog indicate that both effects shape the Milky Way's trajectory, helping explain features seen in the cosmic microwave background dipole. JWST adds depth to this picture by observing galaxy clusters in their early stages of formation. These images show that large-scale structures began assembling when the universe was only a few billion years old. By comparing early clusters with modern ones, astronomers refine models of gravitational flow across cosmic time. The path to these discoveries required persistence. For decades, dust in the Milky Way obscured key regions of the sky, limiting progress. Infrared and radio surveys eventually revealed thousands of previously hidden galaxies, transforming our understanding of the local universe. Distance measurements also evolved. Edwin Hubble's early use of Cepheid variables laid the foundation. Later, type Ia supernovae extended distance measurements across vast scales. Each advance sharpened maps of galaxy flows and the gravitational pathways that guide them. Today, astronomers combine redshift surveys, precise distance indicators, and large-scale simulations. Together, they reveal that the Milky Way is not drifting aimlessly. It is moving along a coherent path shaped by attraction and repulsion across the largest structures known. NASA summarizes this motion by noting that the local group moves at several hundred kilometers per second relative to the cosmic microwave background. Part of this motion arises from gravitational influences within Laniakea, and part reflects the deeper structure of the universe itself. The Milky Way's journey unfolds within a vast cosmic landscape of superclusters, filaments, and immense empty regions, and it is this environment that ultimately defines the motion of everything we call home. Part 9. Are we moving faster because we live inside a giant cosmic void? A striking possibility emerges when we take a step back. Our entire view of cosmic motion and the universe's expansion may be subtly shifted simply because the Milky Way resides within a region that contains far less matter than average. This idea came into focus as astronomers began mapping the universe on scales large enough to reveal the cosmic web, an immense network of filaments and bubbles stretching hundreds of millions of light-years, where galaxies cluster along walls and voids lie between. In the 2000s and 2010s, research groups identified an unusually large underdense region, now called the KBC void, named after Keenan, Barger, and Cowie. Measurements of galaxy brightness and density suggested that the local universe might not match the average density predicted by cosmological models. If our region indeed contains significantly less matter than the cosmic mean, the gravitational pull around us would be weaker. This subtle shift alters how galaxies move relative to one another and influences how we interpret the universe's expansion. Earlier surveys paved the way for this insight. The Sloan Digital Sky Survey, launched in 1998, created enormous three-dimensional maps of galaxy distributions. These maps revealed filaments stretching across hundreds of millions of light-years, punctuated by enormous voids containing only sparse galaxies. The KBC void overlaps the region where the Milky Way resides, raising a provocative question. Could our location inside this giant cosmic bubble subtly bias measurements of local motion and expansion? Multiple lines of evidence support this possibility. Galaxy number counts indicate a dip in density extending outward for roughly 300 million light-years, before returning to the cosmic mean, a pattern exactly as predicted if we occupy an underdense region. Redshift measurements offer another clue. When astronomers calculate the Hubble constant using nearby galaxies, they obtain a value slightly higher than that measured from the cosmic microwave background by the Planck mission. This discrepancy, known as the Hubble tension, may be influenced in part by local underdensity. In regions with lower matter density, gravitational deceleration is weaker, allowing the local expansion to proceed slightly faster. To understand how a void affects motion, consider gravity within such a region. With matter sparse, gravitational pull is uneven. Galaxies near the void's edges can be drawn outward toward denser regions, creating coherent flows across vast distances. Observations suggest that the Virgo cluster, the Great Attractor, and the Shapley concentration all lie outside our local underdense region. Their combined pull, along with the void's relative lack of gravity, contributes to the Milky Way's motion. The concept of gravitational flow was strengthened by the cosmic flows surveys, which measured distances to thousands of galaxies using techniques such as the Tully-Fisher relation and Type Ia supernovae. Comparing these distances with redshift data revealed deviations from uniform expansion, mapping coherent flows that point outward from underdense regions toward dense clusters like Virgo and Laniakea. Another compelling line of evidence comes from three-dimensional reconstructions of the local cosmic web. Using galaxy surveys and machine learning algorithms, astronomers mapped density variations, showing the Milky Way located within a lower density region, bordered by massive filaments. The cosmic web resembles a giant foam, walls and filaments of galaxies surrounding emptier voids, with our position just inside one such bubble. While our position is not unique, it may be significant enough to subtly influence local measurements of expansion and motion. The idea that local structure affects cosmological measurements gained further traction with JWST. By observing distant galaxies with extraordinary clarity, JWST revealed populations of early galaxies that were far brighter and more massive than predicted. These observations prompted astronomers to re-evaluate models of galaxy formation and cosmic expansion. While JWST does not directly confirm the KBC void, its findings underscore how assumptions about matter distribution shape our understanding of the universe. Historical progress on voids began in the 1980s, when redshift surveys first revealed giant, empty regions. The discovery of the Boötes void in 1981 stunned astronomers, as it contained far fewer galaxies than expected. This finding opened the door to the understanding that the universe is not uniform, but structured with dense clusters separated by vast emptiness. Subsequent infrared and radio surveys, including the 2-micron all-sky survey, 2MASS, and Alfalfa, mapped galaxy distributions that hinted at large underdense zones around the Milky Way. Even the cosmic microwave background offers clues. NASA's Wilkinson Microwave Anisotropy Probe and ESA's Planck Observatory mapped minute temperature variations across the sky. One anomaly, the so-called cold spot, sparked discussion over whether it could be caused by a massive void along the line of sight. While debate continues, it illustrates how cosmic voids could leave detectable imprints on observations. Even if the KBC void does not fully resolve the Hubble tension, its presence subtly influences how astronomers interpret local motion. Sitting in a region of lower mass, the Milky Way experiences stronger relative gravitational pulls from surrounding structures. This alters the baseline for measuring our galaxy's velocity and produces small but measurable differences with modern instruments. Such precision requires careful distance calibration. Astronomers use Cepheid variables, stars whose brightness varies predictably, to measure distances within tens of millions of light-years. Beyond that, Type Ia supernovae serve as standard candles, allowing measurements across hundreds of millions of light-years. Combining these distances with redshift data enables researchers to detect anomalies in galaxy motion, revealing underlying density differences. Finally, Gaia has contributed significantly. Its stellar catalog allows astronomers to map the distribution of mass in our immediate cosmic neighborhood, helping place the Milky Way within the local density landscape with unprecedented detail. Taken together, these methods paint a compelling picture. We may indeed reside within a giant cosmic void, a subtle factor that shapes the motions of our galaxy and the universe around us. Part 10. What does this relentless motion mean for the far future of the solar system? Gaia's measurements reveal that the Milky Way's dark matter halo interacts with structures around it, subtly influencing the shape of local cosmic flows. These data reinforce the idea that our galaxy does not sit in an average region of the universe, but rather in a transitional zone of lower density. Over billions of years, matter accumulates along filaments while voids expand, creating coherent flows. The Milky Way's movement toward denser regions and away from emptier ones aligns perfectly with predictions from simulations. This ongoing motion matters not just for speed, but for what it leads to over cosmic time. The solar system's current journey, sweeping around the Milky Way at roughly 230 kilometers per second, is the opening act for everything that will happen to the Sun, Earth, and the planets across billions of years. Long-term simulations show that this motion guides encounters, shapes the galaxy's evolution, and determines how the cosmos will appear to any distant observer far in the future. Early computational models from the 1970s could track only a few thousand stars, hinting at repeated gravitational interactions that slowly alter the galaxy's structure. Today, modern simulations track millions of stars and vast clouds of dark matter, revealing how galaxies change shape, merge with neighbors, and respond to tidal forces. Through it all, the Sun's orbit transforms alongside the Milky Way itself. The Sun follows a nearly circular path around the galaxy, completing a revolution roughly every 200 to 250 million years. Since its formation, the solar system has completed only about 20 such orbits. Gravitational encounters with nearby stars, giant molecular clouds, and the galaxy's spiral structure have subtly altered this orbit over time, and will continue to do so. Occasionally, stars pass close enough to influence the outer reaches of our solar system. One example is Schultz's star, which passed within about 1 light-year of the solar system roughly 70,000 years ago. Its gravity likely nudged a few comets in the Oort cloud, though the planets remained unaffected. Future encounters will continue as Gaia's catalog predicts, gently shaping the distant fringe of the solar system. Over the next few billion years, the Milky Way will approach the Andromeda Galaxy, currently some 2.5 million light-years away. Moving toward each other at roughly 110 kilometers per second, these two galaxies will begin to interact in about 4 billion years. This is not a cataclysmic collision. Stars are so far apart that direct impacts are unlikely, but the combined gravitational fields will pull stars into long tidal streams. Eventually, the Milky Way and Andromeda will merge into a single galaxy, sometimes called Milkomeda. During this merger, the Sun's orbit will change dramatically. Simulations show possibilities ranging from a wide, elongated orbit to a path along tidal streams. Earth will continue to orbit the Sun, but the solar system's trajectory through the galaxy will look entirely new. Meanwhile, the Sun itself will evolve. In roughly 5 to 7 billion years, it will expand into a red giant as hydrogen fuel in its core runs out. Mercury and Venus will be engulfed, and Earth's surface will become inhospitable. As the Sun loses mass through powerful solar winds, the planet's orbits will drift outward slightly. Eventually, the Sun will shed its outer layers, forming a planetary nebula, and settle into a white dwarf stage. The remaining solar system will orbit this faint stellar remnant. Beyond the solar system, Milkomeda itself will continue evolving. Interactions with smaller satellite galaxies will reshape orbits, and over trillions of years, Slow gravitational diffusion will scatter stars into new paths, some inward toward the galactic center, others outward into the halo. Meanwhile, cosmic expansion accelerates under dark energy. Distant galaxies will recede beyond the cosmic horizon, leaving only the merged local group gravitationally bound, creating a long-term cosmic isolation. The distant future of the solar system is one of quiet transformation. Stars exhaust their fuel, star formation slows, and galaxies come to be dominated by white dwarfs, neutron stars, and black holes. Yet, even as the universe fades to darkness, the solar system, or what remains of it, will continue its orbit, a small but enduring thread in the vast cosmic tapestry. These predictions are grounded in careful observations. Stellar evolution models match stars seen in clusters of different ages. Galaxy merger simulations align with images captured by Hubble and JWST. Dark energy measurements correspond to patterns seen in supernova surveys and the cosmic microwave background. Together, these data form a coherent narrative. The solar system's present speed, its path through the Milky Way, the future encounter with Andromeda, and the slow evolution of stars are all stages of one continuous cosmic story. What we measure today is not a fleeting moment. It marks the beginning of changes that will unfold over billions and trillions of years, shaping the future of the Milky Way and every star bound within it. Thank you for staying with this story to the very end. Wherever you are listening, I hope this journey has brought a moment of calm, wonder, and gentle curiosity. May your night be peaceful, and your rest deep.